Basic Vibration Analyst, Setting Alarm Limits, Techniques to Monitor and Control Machinery Vibrations. Importance of alarm limits, objectives of alarm limits in vibration analysis. Alarm limits in vibration analysis are critical for predictive maintenance and machine health monitoring. They serve as thresholds that indicate when a machine's vibration levels exceed acceptable norms, signaling potential mechanical issues such as imbalance, misalignment, or bearing defects. By setting proper alarm limits, analysts can detect early signs of failure, reduce downtime, and prevent catastrophic breakdowns. Alarm limits also help prioritize maintenance actions, ensuring resources are allocated efficiently. Without these limits, organizations risk operating machinery under unsafe conditions, leading to increased repair costs and production losses. Understanding how to set and interpret these alarms is essential for any vibration analyst aiming to maintain reliability and operational efficiency. This presentation aims to provide a comprehensive understanding of alarm limits in vibration analysis. We will explore the ISO standards for setting alarms, including their practical application and inherent limitations. Additionally, we will delve into advanced alarm techniques such as band alarms and envelope alarms, which offer more precise fault detection capabilities. By the end of this session, participants will be equipped with the knowledge to implement effective alarm strategies, interpret vibration data accurately, and apply best practices to enhance machine reliability. Real-world examples and diagrams will be included to illustrate key concepts and ensure practical relevance. Overview of ISO standards, how to use ISO standards, limitations of ISO standards. The ISO 10816 and ISO 20816 series provide guidelines for evaluating machine vibration severity. These standards classify machines based on size, type, and operating conditions, assigning acceptable vibration ranges for each category. Alarm limits are typically defined in terms of overall vibration velocity, mm/s, or displacement, with zones indicating normal, alert, and danger levels. For example, Zone A represents acceptable vibration, Zone B suggests caution, Zone C indicates unsatisfactory conditions, and Zone D signals immediate corrective action. These standards offer a universal framework, enabling consistency across industries and simplifying communication between maintenance teams and equipment manufacturers. To apply ISO standards effectively, start by identifying the machine category and operating speed. Measure overall vibration levels using appropriate sensors and compare the readings against ISO-defined zones. Establish alarm thresholds corresponding to zones B, C, and D for early warning and critical alerts. Integrate these limits into your condition monitoring system to automate notifications. While ISO standards provide a baseline, they should be complemented with machine-specific data and historical trends for greater accuracy. Regular calibration and verification of sensors are essential to ensure reliable measurements and compliance with ISO guidelines. Despite their widespread use, ISO standards have limitations. They primarily focus on overall vibration levels, which may not detect localized faults such as bearing defects or gear damage. Additionally, these standards assume steady-state operating conditions, making them less effective for variable speed machinery or complex systems. ISO guidelines also do not account for machine-specific tolerances or environmental factors, which can influence vibration readings. Therefore, relying solely on ISO-based alarms can lead to missed detections or false alerts. To overcome these limitations, analysts should incorporate advanced techniques like band and envelope alarms for more granular monitoring. Advanced alarm techniques, band alarms, envelope alarms. Band alarms focus on specific frequency ranges within the vibration spectrum, allowing analysts to monitor components such as bearings, gears, or shafts individually. By setting thresholds for these bands, it becomes possible to detect faults that do not significantly affect overall vibration levels but indicate localized issues. For example, a band alarm targeting bearing frequencies can reveal early signs of wear before they escalate into major failures. Implementing band alarms requires spectral analysis and knowledge of machine dynamics to identify critical frequency bands. This approach enhances diagnostic accuracy and supports proactive maintenance strategies. Envelope alarms are designed to detect high-frequency impacts associated with bearing or gear defects. This technique involves demodulating the vibration signal to isolate repetitive impact patterns, which are often masked in the overall spectrum. By setting alarm limits on the envelope signal, analysts can identify early-stage faults that traditional methods might overlook. Envelope analysis is particularly effective for rolling element bearings, where defects generate characteristic frequencies. Implementing envelope alarms requires specialized software and an understanding of fault frequencies, but the benefits include improved fault detection and reduced risk of unexpected failures. Best practices for setting alarms. Case study: alarm implementation. Effective alarm management involves combining ISO standards with advanced techniques like band and envelope alarms. Start by establishing baseline vibration levels and historical trends for each machine. Use ISO guidelines for overall alarms and supplement them with band and envelope alarms for critical components. Regularly review and adjust thresholds based on machine condition and operating environment. Implement automated alerts and integrate alarms into predictive maintenance systems for timely interventions. Training personnel on interpreting alarm data is equally important to ensure accurate diagnosis and corrective actions. A manufacturing plant implemented a multi-tier alarm strategy combining ISO-based overall alarms with band and envelope alarms for critical rotating equipment. Initially, ISO alarms provided general monitoring, but frequent false alerts prompted the addition of band alarms targeting bearing frequencies. Envelope alarms were later introduced to detect early-stage bearing defects. This approach reduced unplanned downtime by 30% and extended bearing life by 20%. The case highlights the importance of customizing alarm strategies to machine-specific conditions and leveraging advanced techniques for comprehensive monitoring. Let's summarize and key takeaways. Alarm limits are essential for effective vibration analysis and predictive maintenance. ISO standards provide a foundational framework, but their limitations necessitate the use of advanced techniques like band and envelope alarms. Combining these approaches ensures comprehensive monitoring, early fault detection, and improved machine reliability. Best practices include setting machine-specific thresholds, integrating alarms into automated systems, and continuous training for analysts. By adopting a layered alarm strategy, organizations can minimize downtime, reduce maintenance costs, and enhance operational efficiency.